Okay, hello everybody to this week's ISGC seminar. This week's speaker is Antonio de Felice. He got his PhD in 2005 from Syracuse University in the USA. And since 2013, he's associate professor at the Yukawa Institute for Theoretical Physics at Kyoto University. He will talk to us about embedding lambda ЛsCDM into VCDM. Thank you very much for giving the talk. The stage is yours.
Thank you very much, Torben, for the invitation, and I'm happy to see also good people in the audience. So it's yes, it's my pleasure to give you this talk about this idea of embedding lambda LsCDM into VCDM. This is a work that I've done in collaboration with several good people, Professor Carso, Di Valentino, Kumar, Nunes, Sulke, Vasquez, and Yadav. And this work has appeared in the archive in these two recent papers. Okay, so this talk is going to talk about tension cosmology, in particular an attempt to try to solve them. Something that must be kept in mind is that the measurement of H0, it's from supernova is model independent. What it means in particular is that all the models, in principle, should agree on that values. If they don't, for some reasons, then the models feel strong constraints. Instead, the constraint on CMB and the growth of structure do require a model in order to fit the data. And so what it means that different models may have different values for their parameter best fit, for example. And this will not necessarily be in contradiction with each other, actually. In that case, what is important is to find the chi-square, so how well the model fits the data. But suppose there are no error in the data, and maybe this is a big statement. What I mean by error, of course, we may have uncertainties, but we don't have, what I mean is that there are not big systematics that people have not considered. So if really no error is in the data, then lambda CDM is ruled out by phi sigma. So what it means, all right? So this is a big assumption. On this assumption, then that's the consequence. In that case, of course, new physics is necessary. When I say new physics, it just means that something different from lambda CDM is then necessary to be the real theory. On the other hand, which theory has to replace lambda CDM is not clear. Of course, then data should break degeneracies among models, and in particular, this is a tension, if confirmed, may actually bring some good insight into the possible ways into the different path we can follow. So let me talk about lambda LsCDM. I would call this one a very promising conjecture, and I tell you conjecture why in a second. And this was introduced by Carso, Escamilla, and Vasquez some time ago. So what this idea is about is that at the redshift about 2, there is a rapid, actually they implemented an instantaneous transition from an ADS ADS cosmological constant, a negative cosmological constant, to a positive cosmological constant, opposite in sign. This was the idea, and people studied how this idea can, what this idea implies in terms of data. But in general, there are challenges in identifying a concrete physical model which can accommodate this transition. Let me tell you why I'm talking about challenges. So what we want is an increase of the cosmological, or the effective cosmological constant from a negative sign to a positive sign, what we call a mirror transition from some negative quantity to opposite sign positive quantity. And usually when we have, so what we have is an increase of some energy density. So usually this leads to some problem, and the reason is the following. So suppose that we have a cosmological, the standard Friedman equation where rho is the sum over the whole matter species, and rho x is a dark energy component. Assuming continuity equation to hold, then we would expect rho x to satisfy this equation. And the fact that we have an increase of the energy density of x implies that this quantity must be positive, but then we need that rho x plus px must be negative. So we have a violation. Typically, we have a violation of the weak energy condition. Here, this curly row is just different normalization for the standard energy density. So what does it imply here? Okay, the first of all, but let me first discuss a second this. We go from a negative energy, negative cosmological constant, to a positive one. Rho x here, it's a component, but you can think of it as maybe the sum of two components, in which one part it's a bare negative cosmological constant. Okay, so the cosmological constant in the unit will be negative. And then there is the, and then there is another component which actually increasing at some point. This increase leads to a rho x, an increase of the total rho x, which will be the sum of these two components, a bare negative cosmological constant plus this dynamical component. In any case, this quantity turns out to be positive. A cosmological constant will not give any contribution, but the part which is actually dynamical would lead to the breaking of weak energy condition. So when this thing happens, usually we may have instabilities, typically ghost-like instabilities. So, and what implies that if we have some instabilities, so your transition may be unstable. And we don't know exactly what implies this, not only to data, but from a theoretical point of view, to what the universe goes through, actually. All right. And the reason why I say that, actually, it's on the other hand, so the fact that we have an extra component leads in the standard law to introducing new degrees of freedom. And introducing, it's very natural to have extra degrees of freedom as soon as you modify general relativity. So then how difficult is to make a rapid mirror ADS-DS transition? And in particular, once we suppose, even we find a model that does the job, and giving this transition in a stable manner, is this transition now, given a model, able to accommodate theoretical and experimental bounds, in particular cosmological tensions? So I'm going to try to answer at least part of these questions. So here the idea is to model the transition is to use minimal theories. So what are these theories? Minimal theories here I will call theories with only 2 degrees of freedom in the gravity sector. So what implies this is that the number of degrees of freedom in vacuum, at least, in vacuum, when I say vacuum, in the absence of standard model component, will be the same number of degrees of freedom as in general relativity. The fact that we have only 2 degrees of freedom implies that we don't have new degrees of freedom, and therefore the particle, the degrees of freedom which would be behind the weak energy breaking condition will not be existing. Therefore, the would-be ghost does not become a ghost because the particle itself does not exist. All right, so this is the idea, right? So the idea here is to use the fact that we only have 2 degrees of freedom, and so that we remove the typical extra scalar, which would become ghost. Evidently, this is a good approach, but we have to make sure that indeed non-stabilities are there, and that the transition is not only not only classically, but mainly so it doesn't lead to any Laplacian instabilities and cosines. So I've been working a bit in this minimal theories of gravity, and the first work I did with Professor Mukoyama, and that was a work on massive gravity, so introducing massive gravity as a minimal theory. This was, at least in my opinion, necessary if we want to make sense of homogeneous and isotropic backgrounds in massive gravity theories, for which instabilities at 3 times were known to exist. For this, because massive gravity would have 5 degrees of freedom, but the minimal theory would have only 2. So there would be unstable modes are removed from the theory itself. Later on, Aoki, Lin, and Mukoyama introduced a construction of minimal theories by means of a Hamiltonian formalism. And with them and Masroor, I studied what these models introduced here were leading in terms of phenomenology. And in particular, we were finding that typically these modes would lead, typically these models introduced here were having a G effective divided by G, which would be different from 1, in particular time dependent. This is not only for this, not only true for the dark matter sector, but also for baryons. And so therefore, this phenomenon would be strongly constrained, at least today. Okay, so let me then introduce this VCDM. So, which is a different approach, although related to that one. So the construction was done in this first paper, and other paper regarding phenomenology properties came out later on. The good point of VCDM does not lead to that constraint dynamics for G effective. That's one of the points. So because of that, the phenomenology becomes a bit larger. Parameter space becomes larger. So the idea is that we only have gravity and non-propagating fields. You can call Lagrangian multipliers. So the gravity action without standard matter fields is given by this part, which is the standard Einstein-Hilbert written in ATM variables. And then we have this Lagrangian multiplier phi. So this non-propagating field phi, lambda 2, and lambda. All right, so one can show that indeed this theory does not have propagating degrees of freedom because the scalar here does not get kinetic terms. So then, okay, seems okay, but then what is the, okay, so, but we had to pay a price, okay? So it's true that we may have now an object which may have some dynamics because you see this one says that nabla square for the special metric is 0. So in particular, phi could be a function of time. And then we have an effective dynamical component, all plus other contributions. But in any case, so this construction here would not add degrees of freedom. Okay, so although there is, you may say, oh, there is a scalar, another scalar, another scalar, but when we count the propagating degrees of freedom, only tensor mode remains. These are all non-dynamic. The price to pay, as you can easily see, is the breaking of for the difference. In principle, one could introduce a Stuckelberg field to restore time-like Stuckelberg field to restore for the diffio, but that time-like scalar field will get a VEV, which is, you know, say phi equal to t, and leading to this Lagrangian here. So what it means that so we will have a preferred frame in which yes, this scalar say is a function of this one by solving this equation can be a function of time up to boundary condition. Okay, so if we study that theory in terms of homogeneous and isotropic background, we find these equations here. And in these equations here, notice that rho I here are, I stands for components, standard matter fields components, okay? So these are the all standard ones, which, you know, satisfy continuity equation. And then we have this equation here, which relates V with this energy density. And also the dynamics for phi given rho plus p, where rho is the sum of all the rho I, and p is the sum over all the pi. Yeah, so this is if-all variable. I assume here h to be different from 0, so we can rewrite it into this form. We can rewrite these equations as standard Friedman, where rho phi is given by this expression. And there is also a relation between h, phi, and v phi given by this. Okay, so therefore, the idea now is that this rho phi, it's a dynamical component behind which there is no propagating degrees of freedom. So this rho phi can increase. Rho phi dot could be positive, but And you may say, okay, then weak energy conditions are violated, but there is no scalar which becomes unstable because there is no particle behind it.
Antonio,
Okay. Yes.
can I ask a
Hi,
question?
Rio.
Hi, how are you?
Good, good. How are you?
Good. So, how general is this theory to have like 2 degrees of freedom? So to my knowledge, this construction is kind of ad hoc. Is there any way to like construct a theory with only 2 degrees of freedom? Let's say if you introduce like vector-like component rather than scalar-like, which is phi here.
If you introduce,
Yeah. So can you construct how general is this theory to have 2 degrees of freedom, only 2 degrees of freedom?
yeah. So okay. So so here, no matter the potential, see, we have only free function. So no matter what the potential is, we will always have 2 degrees of freedom. Now,
Right.
if you look for some other theory with 2 degrees of freedom, yes. So one may. So there are different possibilities. In particular, so for example, one thing that one can do, for example, is to, for example, to make a coupling with phi with some other fields, the same phi here. For example, you can couple it to a dark matter component. That theory will still have 2 degrees of freedom, but that theory will have a non-trivial consequence for dark matter. There are other ways. For example, another possibility would be, for example, the cascaton. There are several other possibilities. For example, also the one mentioned before, but somehow, I'm sorry, I mean, something. Yes, so for example, yes, people introduce here other possibilities. Mukoyama-san also introduced other possibilities with people in Paris. So there are several possibilities. Yeah, there are several theories. This is probably one of the simplest.
I see.
And yes, so in particular, something that maybe can be said is that phi here, notice this is already, this action already breaks explicitly for the D field, although preserves 3D D field and timely parametrization invariance. But how can I say? So this is not the Stuckelberg field. The Stuckelberg field has already gotten a VEV. So this phi here does not necessarily be time-like. For example, phi could be constant. And still you will have 2 degrees of freedom, actually. So this phi to be constant, so in this sense, it's easier to find solution. For example, static configuration are consistent with phi to be constant. Of course, when we say phi to be constant, then phi is constant everywhere. So, but because we have a preferred frame, actually, on which, cosmological frame where phi is time dependent, then phi should be time dependent everywhere. But in any case, so neglecting this time dependence on solar system scales, it's not difficult to find solutions which stars and other things like that. So in terms of phenomenology, this theory seems to be not so complicated like others. You notice, for example, the cascaton phi, so one is bound to have a time dependence always on any background. So then what it means actually is that, for example, static configuration are not allowed. So you see what I mean? It's a bit, but anyway, in any case, so.
I see. So, okay. Thank you. I think that's the point.
Thank you very much. All right, so we're at this one. Somehow there is some unpredictable behavior in my slides transition. Indeed. Okay, so right. I'm sorry, it's not, I'm not getting. All right, so I was here. Okay. Yeah. Okay. Yes, so we're getting this equation, this effective Friedman equation. And of course, I am not understanding what's going on.
Maybe you can simply stop once the screen sharing and then restart it again.
Okay, something. Oh, it's actually the slides are a bit screwed up. Okay. Okay, so I was here. All right. Yeah, I'm not understanding what's going on actually. Okay, let me stop sharing. Yes. Okay, let me try to. It. All right, so yes, so how do we implement then a fast transition? Okay, so this was the first work I wanted to talk about. Okay, so in lambda sscdm was this theory, which let me tell you how it was a instantaneous change of the cosmological constant at some parameter a dagger, a being the scale factor. You see there is a switch of sign which is instantaneous. And so this is at the level of background. So in VCDM, rho phi, this phi which doesn't have degrees of freedom behind, is if I write in terms of an effective cosmological constant, if I set this one to be constant, then if I solve for the potential, this is what we get. We get a linear equation in terms of phi with this constant here, where alpha is totally free. So we can actually implement a smooth sigmoid transition through this S of phi. When phi is much larger than phi c, you notice this becomes 1. And then what is after a transition, we will have an effective cosmological constant lambda ds. For phi much less than phi c, now this quantity will go to 0. So this term goes away, and the v of phi is approximately given by this, where the cosmological constant is negative. you notice that this potential it chose by hand actually, where alpha after and alpha before transition are free parameters, together with this eta, which tells us how fast the transition is. Okay. Now, let me explain at least two ways to implement the transition. Okay, the first one is, let's assume to give this free function v of phi from the beginning. Then we need to give a initial condition, for example, the value of field today, in this way, where alpha a after it's a free parameter. We can set it to be 0 if we want. And then the dynamical equation implies this. Now, this is phi as a function of z, the redshift. Rho and p is the total rho and p for the non-matter fields, for which we solve the continuity equation. We know rho plus p for the standard matter fields as a function of the redshift. And h instead is given by this. So for a given potential, in principle, we can solve this differential equation knowing phi. And once you know phi is a function of z, we have v as a function of phi, which is a function of z. And then knowing phi as a function of z and v as a function of phi, then we will know what is h as a function of z. But there is another way, which is simpler in a sense, which is, okay, let's give from the beginning what is rho phi. And because we know what is rho phi, then as a function of a, and we know continuity equation for standard matter fields, we will know what is h as a function of a over redshift. So then we have h of a, and we have also h prime of a. So we don't have to solve any ODE to know what is h of a. And this is very useful when we do Monte Carlo sampling. But we should solve an ODE when we want, if we want to reconstruct the potential. In particular, we will have this Friedmann equation. And then now this dynamical equation is thought as h is given function of z. Giving some initial condition, we can solve for phi. And then giving phi and the standard matter density in terms of redshift, we can write v as a function of redshift. So we know v in terms of parametric form, the potential in parametric form. So this is just saying that we can reconstruct the transition, the potential, after we give how rho phi, the component, the dark component, would make the transition. So in particular, we studied a few cases of transition, what we call quiescent transition, agitated transition. So you notice that phi linear, v as a function of phi linear, would give cosmological constant. So the change in slope here just says that we go through two different cosmological constants. If we study what is rho phi, we will get this kind of jump where we go from a negative cosmological constant to a positive one, mirror transition, in this form, okay, which is, we call it quiescent, which means like calm. Huh? Instead, if we make, for example, this is evidently another transition, another possibility, where v goes from -1 to 1. And in this case, if we plot what is rho phi, we will get this bump here. Again, the cosmological constant will go from a negative value to a positive value, but in the middle, there is this bump. So you may imagine that we can open here a phenomenology of transition, where the transition can do very, different things, actually. These are two cases, but you understand that there could be others. So how to understand which transition is, is good in our case or not? Well, the only thing that I can think of is to look into the data. Because from the theory point of view, this V of phi is a free function. There is no instability problem. So what then we can do is to look into data and see whether the data can distinguish transitions. In particular, are there transitions which are ruled out? And are the data able to distinguish between different transitions or not? All right. So what we are going to study now is the difference between lambda CDM, lambda VCDM, lambda S VCDM, and lambda CDM. Lambda CDM does not need any introduction. Lambda S CDM, it's, again, an instantaneous change of the sign of cosmological constant. The model is not given of such a transition. The background only is modified instantaneously. And in particular, because they didn't have any model, they were considering GR dynamics for perturbation everywhere, before, after, and during this instantaneous transition. Lambda S VCDM instead, so in our theory, we cannot allow for an instantaneous transition because the scalar field would not have a well-defined derivative there. So we had to smooth out this instantaneous transition into a fast transition in the sign of the cosmological constant. In this case, the model is given. So the background is modified through a continuous and differentiable way. And indeed, we will have, because the model is given, we can actually study the dynamics for the perturbation. And so we can, this is a tool to study really the physics of transition. Okay, so now what we're going to talk to today is to understand how the model and these three theories, fit the data. Lambda CDM is just like to make to set like the standard case and see how the other two, lambda SCDM and lambda SVCDM, will affect the data. In particular, we're going to study the Planck data, the latest BAO also, Pantheon, Shoes, and KITS 1000. So how do we implement this? All right. So we need to confront the theory of the observation. So we will, for simplicity, so we will only assume a smooth quiescent transition. So what we are going to give explicitly how this effective cosmological constant, or if you want to rho phi, changes with the scale factor in this way. So we have a quiescent transition, although it can be fast, right? Because we set to zeta to a constant value. And the reason why we set it to constant value is to have the same number of parameters with lambda S CDM, for which we had an instantaneous transition. If you want infinitely fast transition, in our case, we set to a fast transition, but finite. You notice also, okay, so this is the background, how the background is modified. This modification of background leads to modification of the perturbation equations. In particular, the Newtonian the curvature potential, phi. This is the second Bardeen potential, and this is the Newtonian Bardeen potential. So that's the dynamics of phi. And in generativity, this object will be 1. This gamma would be 1. In this theory, actually, it's given by this term here. And now you can see when this quantity goes to 0, so if there is no transition, of course, gamma becomes 1, and then we go back to generativity. But if this derivative is non-zero, in particular, it becomes large, right? Because lambda s, when you take the derivative, will get, some component related to the rapidity of transitions. This may actually become large. So this may affect gamma, suppressing the denominator or even changing it, changing the sign of it. Okay, so then some modification enters here, and everywhere phi, capital phi dot, is present. For example, in the cold dark matter component. Also, barium will have a similar modification. So, okay, let's go into the result. Now, let's study the data. Here, what I imposed that, suppose we study only Planck, right? Planck alone without anything else. Lambda CDM gives the famous 67 something with a chi-square of this form. This lambda SCDM is the model which has instantaneous transition and no modification in the perturbation equation. So we get an increased value, right? And then we will have Z dagger is the redshift at transition, and chi-square reduces, all right? So that's an interesting kind of direction. If you put lambda S VCDM, the best fit inside our chains is 73.4, which is also very close to the mean value. And then we will have a scattering, and we are going to discuss in a second what this means. And then Z dagger, it's about 1.88 plus or minus, and the chi-square further reduces a bit. So this is interesting. So it's, well, I was very surprised about this value, which is, very good fit with the, you see, this plot here is the shoes data, actually. We're going to discuss in a second about this one. But what we can see already from the plot is that lambda CDM, yes, it's outside, but this quantity, which would be the VCDM, is as a larger, so the parameter space is spread out on a larger area. So as you can see, it's 73.4, negative 4 plus 1. So what it means, this one? It means that we have a minimum, but the minimum is not so peaked. So if you want, the chi-square difference is not so large, so that, the model can exclude strongly the H naught. Because if you remove minus 4, as you see, you go already at 69. So what it means that it's interesting, but so the best fit is here, the best fit is here, but we would probably need other data similar, consistent with Planck, for example, Atacama results, to try to remove degeneracy in this parameter space. But in any case, the result is at least promising and interesting. This is the age of globular clusters. So this is a 1 sigma contour. You notice that, yeah, there is a little bit of tension, but not significant, because this is just 1 sigma. But it's also promising in terms of this model, which seems to be completely, you know, it gives a nice prediction for the age of the globular clusters. All right. So, of course, what we notice is evidently differences with ΛsCDM, but there is also difference between these two models. Remember, this one has a model with perturbations equation, and plus the transition of the background is not instantaneous, but is smoothed out. So I would like to understand better where this difference comes from and which role they play different things. But the good point is that embedding this theory into a model, which we call lambda as VCDM, does not spoil the phenomenology. Okay, so indeed, the phenomenology is not that different. In particular, it's this line here is not totally inconsistent with that, right? So there is at least some model. This shows that there are some models which can implement this rapid change of cosmological constant without screwing up the data. Okay. What also it's interesting is that so here we can see that so omega m respect to this one tends to be slightly less, and both are slightly less than ΛsCDM. Sigma 8, you notice here there is an increase of sigma 8. We will see what happens in S8, but you notice that omega m decreases and sigma 8 increase. So the whole thing must be treated with care when we do S8, which is a combination of that. And also in terms of this Z-dagger, you notice that for this theory, we have a 1 sigma contour, whereas ΛsCDM does not have 1 sigma constraint, and it's a bit shifted towards these values here, okay? But the best fit, it's 1.88, right? So we are about here. Okay. So what we learned from this one is that embedding the theory, the idea of ΛsCDM into a model leads to consequences. It's not that we just get the same thing, but we get actually some difference. And we would like to understand why. In particular, is that because of background dependence? So there is a difference in background because ΛsCDM is instantaneous, whereas this one is smooth. Can different transition dynamics lead to different fit to the data? So we studied the quiescent transition in the dark energy component, but we would like to understand what happens to the fit when we use, for example, an agitated transition. And what about dependence on the perturbations equation? So this perturbation equation feel the change as a kick. So at some point, phi dot will increase or decrease substantially because of this background rapid change. So this will change, it's like changing the, if you change the slope, it's like changing the initial, initial conditions at some point for your field, actually. And what this leads to, in particular, to some possible deviation of the observable because of this modified dynamics for the perturbations. So what also it says that, in principle, as I said, this is an implementation of this change of the sign of the cosmological constant in one model, but we can use other models, and then each model will have a different, maybe same background, but different perturbation dynamics, and will be interesting to understand how different models perform in terms of fitting the data. But in general, what happens, the contribution between background and perturbation are entangled. Background changes, and background changes the perturbation equation, and the perturbation equation in turn may give a better or fit to the data, and the whole thing are entangled. So it would be interesting to disentangle the two contribution. How to disentangle this one? For example, we can modify the background lambda SCDM so that instead of being instantaneous transition, we have a smooth transition. But still using the GR equations of motion for the perturbation. You may say that this approach maybe is not theoretically motivated, but it will make us understand what is the contribution of the background or the perturbations between these two models. Yes, so this is a work in progress. So if we add other data sets, so before was everything in terms of H0 Planck alone. So what if we add data, other data? All right, so we add the different data, and in terms of chi-square, so ΛsCDM is this, and you notice that there is a decrease of a chi-square, which means best fit to the data for this model here, which is, you notice also the transition is tendentially always a bit better than. So it looks like lambda SCDM gives a better fit, and lambda VCDM has a further improved, at least when we use BAO. When we start using all the data, this difference between lambda SCDM and lambda VCDM tends to reduce, okay? At this point, essentially they perform exactly in the same way. Yeah, notice I use Pantheon plus using everything all together, then we go back to the same result. But it's interesting at least that there is this tendency in lower or equal in terms of chi-square. If we add all data set, this the plot, so it's a bit chaotic, but essentially what happens is that yes, we will have a different plotting regarding the fit, and you see if we add everything, we tendentially get this one, which is you notice Planck really was going to 73 point something. So in a sense, Planck was in a very good agreement with Schu's data in lambda VCDM. So what about S8? As I said at the beginning of the talk, how many minutes am I left with?
Well, since we had quite some interruption, I would say like maybe 10 minutes.
Okay. All right. So what about S8 tension? Now, as I was saying at the beginning of the talk, the Schu's constraint on H0 is model independent, okay? And the fact that we have Planck alone giving 73, it's very nice. But S8 constraints are actually model dependent because this is just a fit to the data that comes from the growth of perturbations. So then what happens is that we had to fit model by model, we should fit the data. And in particular, let's see that in the lambda VCDM, the situation improves with respect to lambda CDM. This is better because the 2 sigma region gets inside here, but you notice that still the error bars are pretty large. So although the tension is reduced, but I think I would look for more data to possibly constrain more the system by shrinking this area. Here, I don't consider what baryon implications, so just set the KITS 1000 data. So at least it's interesting. But okay, there could be more room for theory as well. So where to go next? Okay, so the results are promising. Okay, so the direction of this modification seems to be very interesting. Using Planck-alone data, we get very nice concordance with Schu's data. But we expect new data, in particular to explore or possibly to remove tensions. Also, I would like to understand more the phenomenology of general transition. So this transition being time dependent and background dependent, I want to see what is the change, so how this different transition may fit the data in a different way or not. And when I say this is that, or maybe even in the light of some other theory. Okay, then we would like, yes, so I would like also to study better the CMB data alone. So I would like to understand, to break degeneracy by, for example, as I said before, maybe adding Atacama data or something else which has the same physics to understand exactly how, whether this nice area can be shrink and to which values, lower value of H naught or Schu's values of H naught. Also, global cluster age maybe in the future become very interesting constraint, but so far is not as constrained as Schu's data. We would have also nonlinear observable. What I mean by that is maybe to understand what happens at nonlinear level in terms of you know, embodied simulations, for example. So I reached the conclusion. So a redshift Z approximately equal to 2, we have a rapid mirror ADS into DS transition, which seemed to lead to good fit to the data. So this is promising. And there are challenges in identifying the transition dynamics. What is, the theory does not predict what transition we may have. We just have to, what we can do now is just to ask the data if we can at least remove some possibilities of transition or not. Also, other theories may lead to better fit. So this was an implementation, but it may not be, it will not be unique. So what happens to other theories? Of course, theories which do not lead to instabilities, right? But in the end, we will need future observation to understand better what's going on. Thank you very much, and sorry for the problem I had before. Actually, thank you very much.
Thank you, Antonio, for this really nice talk. Other questions?
I have one question.
Sure.
So Antonio, thank you very much for the talk. So, do you have any idea what is the physical mechanism of the rapid transition of ADS to DS, such that it can alleviate the H naught tension?
Yeah. So yes, in this theory approach, actually, we have given a potential, you know, to lead to that transition, we had to choose a particular potential. Okay. For example, let me go back to. Yeah. For example, something like this. Okay, because what we chose was a quiescent transition like this. So what we had to specify, it's a potential for this non-propagating scalar field, which is of this form. Now you may say, why this potential and not something else? Right? Then I don't have, so if I rephrase your question, I mean, why do you have in particular this transition and not another one? I don't have any particular good reason, actually.
No, I mean, it doesn't matter whether the potential. I mean, even for the lambda ЛsCDM can already alleviate the tension a bit. So my question is basically why this kind of transition can do the job.
I understand. I mean, okay, from the data point of view.
Oh, okay.
Yes. So this is yes. Right. So what happens is that if you have that's a good point, actually. That's a good point. So if you have a negative cosmological constant, if you have an effective negative cosmological constant for longer time, so this is related to the position of this transition. So notice that if you go back too much, okay, so what happens, suppose Z dagger increases, okay? So suppose I shift Z dagger to very large values. Z dagger is the ratio of transition. So what happens in that case is effectively, in terms of today's data, I have more and more lambda CDM.
Right.
Okay, because after that, the cosmological constant is positive. On the other hand, the Z dagger cannot be very close to zero because we have acceleration today.
Yeah.
Okay. So, the theory says that indeed a negative cosmological constant seems to fit well the data in terms of Planck. Or I would say Planck giving larger value of H naught, allowing, because you see this has a large error bar.
Yeah.
So it does not necessarily predict that it's 67, it's 73 exactly, but it gives a spread out thing actually.
I see.
So it's because of that, I mean, it looks like it allows more parameter space rather than preferring H naught to be larger.
I see. Thank you.
Yeah.
Sorry, I think Rio had a question, if I saw it correctly.
Yes.
Yeah. Well, just a quick. Well, you mentioned like possibility of other theories, but is there any other theory that actually successfully implement like this type of transition?
So it's non-trivial, all right? So the answer is it's non-trivial.
Yeah, it's like, I guess so. Yeah, I guess so. It's like if you break the some energy condition, usually it's
Right.
quite.
So only point is that, but I'm okay. Let me put so that breaking of the energy null energy condition is at the level of the background. So what happens at the level of the perturbations? One has to carefully study what, theory by theory.
Right.
So let me put, for instance, as you know, there are some theories which allow W to be less than -1. The effective equation state of dark energy to be less than -1. And again, that is leading to, usually in the standard case, will lead to instabilities. But for example, we know that the Galileo, the cubic Galileo, for example, allows that without being unstable. So there could be, so maybe in an EFT scenario, one could study what's going on in a general case and verify or not whether, you know, you have some no-go theorem or not.
Right. So the no-go theorem by Tsutomu, Kobayashi, that was only for Genesis. I mean, the rigorous proof was only for Genesis. Is that correct? Usually there are problems if you break null energy condition, but the rigorous proof was only for Genesis scenario, not other. Like from Minkowski to,
I see.
You know,
I see.
This type of transition. But now you are talking about the ADS to DS, or negative, positive, negative to positive cosmological constant. So I guess that type of proof doesn't. Well, that proof probably doesn't apply to the VCDM anyway. But it seems quite non-trivial in general. But I guess there is no rigorous proof, I guess, right?
Right. And of course, other minimal theories probably can do it.
I see. Yeah.
But yes, but to be honest, yes. So it's something very interesting, something that I would like to explore. Because if there is another one, you know, I would like immediately see how this new theory is affecting the fit. Because in that case, the background will be totally the same, allowing this background. But then in that case, the only difference comes to the level of perturbations. And then it will be very interesting to see how different theories now behave according to their perturbation dynamics. I don't know. In this case, it seems the fit was a bit better with this dynamics, but it could be others which can further improve or not. So it would be also interesting.
I see. Okay. Thank you. That would be interesting direction to see.
Yeah. So I think, okay, the Costas wrote in the chat, he wrote a question. What other observation would be effective if this transition would take place, or else what other hints should we look for to prove that? Yes, that's okay. It's maybe in the okay, but it's but of course if we had very, very precise data so that we can know H at different values in redshift, then I think this would give, so given an histories of H of Z, that would give strong constraints, not on any model, in particular on this one. Yes, so, but the model here is predictable. So any new data, BAO, whatever, supernova, or whatever other, maybe Atacama, whatever, will have a fit on this one. So what I would say is that to have more precise data would tell us whether the chi-square will be further improving or not from ΛsCDM. Of course, if the model doesn't work, then it means at some point the chi-square starts being bad. So I'm looking for new precise data, especially in the S8 tension, because you see this S8 tension was some tension, milder tension, but still something could be there. So if those areas shrink, then this model will be, strongly constrained. So far seems to be, at least H0 seems to be nice in the light of Planck, but yeah, future precise data will be key. But not only for this model, of course. Of course, if you have more precise data in the future, and a discrepancy in ΛsCDM is there, of course, we will have, also more motivation to look for alternatives. Okay. Oh, okay. Thank you very much, Kostas.
Okay, are there other questions? Maybe I can ask one. When we have more gravitational wave data also from higher redshifts, binary black hole mergers or supermassive black hole mergers, what do you expect to be changed then in your results? Would it become more precise, or are there any difficulties in implementing them?
Yeah. Okay. So that's a very good question. I didn't think about that, but okay, let me give you the answer that I am at the moment in my head. Okay, so the propagation of gravitational waves follows very much so in particular, gravitational waves have no mass. For this case, the propagation speed for large k is equal to 1. So in this sense, if I study, for example, gravitational wave propagating on the cosmological background, I will not see much difference, except, but that I don't know how people will wanna do in the future, because there is an effect in H. So friction term, typically friction term may depend on H, actually, and dynamics of H. So, but I don't know how, if people, how how precise data you need to make this kind of constraint. Probably expect not much in terms of gravitational waves. What I mean, I expect other future catalogs, Euclid, Lightbird, and stuff to give definitely stronger constraints. In terms of phenomenology of gravitational waves, it is very similar to generativity, except for some background dependence in H. So at the moment, I don't think they can compete very much with other data sets.
Would there be some, I mean, we also have black holes, and I guess you would also have in these models, although it's you apply to cosmology in the modified version, you would also have some other black hole types. Do you think if you combine those, you may have the ability, the possibility to infer more about this? That you can maybe say that one part could be excluded by the black holes, and then you of course can draw also some conclusions on cosmology.
Yeah, that's okay. That's a good point. Indeed, I studied with other collaborators black hole solutions, star solutions, and what we saw is that there are solutions. Maybe they're not unique, but there are solutions which are the generativity solution written in a how can I say, in a particular frame. Okay, so this theory breaks for the DD field, so which means that there is a preferred frame, or if you want a preferred choice of coordinates, and this preferred choice of coordinates is compatible with the existence of black holes, for which we have found solutions. And yes, in that sense, black holes would exist, and the space-time around them would be the GR background, with the caveat that in a particular frame. Okay, so it's like in GR would be a choice of coordinates. In this case, instead, it's it's the particular frame on which the theory is defined.
Okay. Yeah. Thank you. Are there other questions? If not, then I would suggest we end the recording and the talk here. Thank you very much again.